Grade 12 Physics, Quantum Note Number 1, Blackbody Radiation. Quantum mechanics is the study of the really small. What is an atom? How does a nucleus exist? How is it possible for electrons to orbit around the nucleus? All of these questions can be solved using quantum mechanics. So at the turn of the 1900s, quantum mechanics was a brand new thing. Before 1900, we had classical physics, which basically describes motion, thermodynamics, waves, electromagnetism. But right around 1900, 1905, new physics came into being that solved some of the problems that classical physics couldn't solve. Those two pieces of modern physics were relativity, which was mostly done by Einstein. That covers gravity and moving near the speed of light. And then there was also quantum mechanics, which was done by three major players: Max Planck, Albert Einstein, and Niels Bohr. Quantum came around through the study of blackbody radiation. Whenever we know from previous units, we know that when we accelerate a charge, it will naturally give off electromagnetic radiation, it will naturally give off light. Because we have a body temperature, all of the particles in our body are vibrating. They're going back and forth, back and forth. The electrons on the particles are also going back and forth, means that also that those electrons are accelerating. Because those electrons are accelerating, we must be giving off electromagnetic radiation. And because of the temperatures of our body, it happens to be in the infrared spectrum. We'd expect that if we increase our temperature, the particles should vibrate faster and therefore give off a higher frequency. If we choose a theoretical piece of metal and we warm it up, if we measure its intensity versus the wavelength we give off, we notice something peculiar. Here, let's say we warm a metal up to about 3000 Kelvin. That's pretty warm. It will give off a whole range of wavelengths, with the maximum intensity being somewhere below the red visible light. If we warm it up to 4000 Kelvin, that intensity peak changes, where now the most intense is going to be red light. If we warm it up again to 5000, we can see the peak changes again to the left, somewhere in a visible spectrum. This explains when something gets warm, it will go from red hot to white hot because it eventually gives off more of the spectrum. We can say though that as temperature increases, so does the frequency of the blackbody radiation. Again, these are just measurements we make on a piece of metal. So it was expected that as frequency goes to infinity, so should the temperature. As something warmed up more and more and more and more, its frequency should keep increasing, increasing, increasing forever. But this didn't happen. Frequency only seemed to go to some maximum value for our metal somewhere near the color blue-purple. It would never increase anymore into the ultraviolet or X-ray spectrum. This was something unexpected by scientists in the day. It was called the ultraviolet catastrophe. We couldn't explain this until Max Planck finally came along. He discovered that if we're actually going to think of light properly, we can't think of it as an energy that's continuous, meaning an energy that's able to freely change from one form into another. We have to think of it as an energy that can only change in discrete packets or discrete chunks. If we compare it to classical, energy can change along a smooth curve, gradually from kinetic to potential, whatever we want. But quantum actually says no, energy can only go in little steps or little chunks. Now the consequence of this is that this is how we're able to actually explain things like energy packets or energy chunks in an atom. Planck went out to ask, though, how small can these little chunks or steps be? He found that the scale at which the little chunks occur at are governed by something now called Planck's constant, 6.626 times 10 to the negative 34. So if we examine a little chunk of this energy, this would be equal to 1 photon of light, where a photon, the energy of it is equal to h, that Planck's constant, multiplied by its frequency. If we compare the energy of a red photon to a blue photon, we can make those calculations. Here, energy equals hf, so our new constant times the frequency of red light, 4.3 times 10 to the 14 hertz. That ends up being 2.85 times 10 to the negative 19 joules. If we compare it to a blue photon, energy equals hf. Here we insert the frequency for a blue photon, 7.5 times 10 to the 14 hertz. And we notice that we get a value that's about 60% larger than a red photon. This means blue light has more energy than red light. As a general sequence, as frequency increases, so does the energy of a photon. This also gets us to explain emission spectra for a certain element. If we take hydrogen, for example, and we excite the electrons, they jump up energy levels, and they release that energy as the electrons come back down. Because the electrons only can absorb certain chunks of energy, the amount that they jump up and down has to be a defined value. So let's say they jump up one orbital. That amount of energy would be a smaller amount, and that's going to correspond maybe to a red color of light. If we make it more excited, they jump up 2 energy levels. That's going to be a certain higher frequency of light, maybe in this case green. If we make it even more excited, it might jump up 3 energy levels, which is more energy than the first 2. That might translate into purple light. So if we excite hydrogen, we only see that certain frequencies are given off because those are the amount or the chunks of energy that hydrogen is willing to accept. So here, if we dissect that light for hydrogen, and you can look this up on the internet, the emission spectra for hydrogen will only have 4 bandwidths. That first energy will be some lower frequency. There it is, 656 nanometers. 2 energy levels will correspond to this greenish color, 486 nanometers. 3 energy levels, 434. And then finally, the largest one would have the smallest wavelength or the highest frequency, 410.